So this is basically the second half of now our fourth unit on further methods of differentiation. We spent the first half of our section talking about how to find the derivatives of sine, cosine, and all of the offshoots of sine and cosine. So that would be your tan, your cotan, your cosecant, your secant. And we would have learned, I know this is kind of a recap here, but we would have learned 6 different rules for all of the 6 main trig identities. And you basically just need to know how to use them. I'm going to give you these formulas on any sort of assessment, which really the only one left is your final, because you could obviously look them up for your assignments. When I was in university, and this is my understanding even for students that kind of relay information back to me nowadays, that you have to memorize most of these derivatives otherwise. So I mean, it's not that it's impossible to memorize, but it takes a little bit of practice to get used to. So if I can give you a couple of reminders of some of the things that I used to remember here, I'll remember that a secant and a cosecant, they both actually contain themselves in the formula. Secant has a secant, but then has the tan on it. Cosecant gives itself a cosecant, but you know how it has the word co in it? Well, then it also has the cotan of it as well. So, yeah, in terms of tan to secant squared and cotan to negative cosecant squared, sometimes you just have to come up with your own little things to help memorize them, but hopefully you're fairly good at those ones so far. My goal over the next couple of lessons now, the next 2 essentially, is to try to teach you how to find the derivatives of other non-polynomial functions. Mainly we're going to talk about how to do exponents and logarithms. Those are the 2 things I want to focus on. And today's lesson I'm going to show you 2 new rules, but I also want to explain to you what natural logarithms are and how that works, because you probably don't have you're probably not familiar with these based on 30-1. So it's a very strange thing, actually. In Math 30-2, they teach natural logarithms, but in Math 30-1, we don't teach natural logarithms. So to begin with, let me show you what a natural logarithm symbol is. It is ln. And we pronounce this natural logarithm, the way you say it is ln. Kind of like your front lawn, like I need to go water the lawn or mow the lawn. And you'll see that on the calculator here, that's this button right here, ln. It's right below the regular logarithm. And you might notice that we can actually infer some clues about how it works here, just based on the yellow superscript kind of stuff that's behind it. See how log goes 10 to the power of x? You might recognize that a log has a base down here in the corner of 10. And you can change this up so that you can have bases of 2 or 3 or 4. But ln will actually have this in the corner. I'm going to clear it off and just press it for you. It's actually e to the power. And that's where I want to begin. I want to talk today about what e is. So before I do that, I'm going to go quite off my notes here and just kind of write some stuff out. In math, there's been discovered that there are very, very few constants. Like, for example, in physics, there are many constants. Like k is a constant, or capital G is a constant in physics. Maybe those are some things that you're familiar with. These are based on gravity and electrostatics. But in math, there are actually a few constants, but there are mainly 5 main constants, and you should be familiar with 3 of them so far. One of the constants is 0, and another constant is the number 1. And really, these 2 numbers make up almost all of the numbers that we're aware of just by combining them somehow. For example, you might say, well, how do you get to the number 242? Well, it's just 1 plus 1 plus 1 plus 1 plus 1 over and over and over again until you get to 242, right? If you were to try to get to a decimal number or a fraction, 32 over 7 is 1 plus 1 plus 1 32 times over 1 plus 1 7 times. And so really, like with the numbers 1 and 0, we can pretty much accomplish most of the numbers we require. But there are some that we can't get to because they're irrational. And one of the best ways of getting to irrational numbers is to figure them out in terms of pi, which is 3.14159, etc. And so that's another constant you may have heard of. So this is just straight up the number 0, straight up the number 1. This is 3.14. And there are 2 other constants that make up the main 5 constants known to mathematicians. And they are e and I. Now, I wouldn't expect you guys to know much about e and I. I you may have heard of as an imaginary number. That's what I believe stands for, is imaginary number. And I know very little about these, other than, from what I understand, this is a rule for it it is that if you were to take the square root of a negative number, it's known as an imaginary number. And I worked with them very briefly in university. I don't remember much about them, but it opens up some of the non-real numbers. If you guys maybe recall from, I don't know, grade 8 through 12, maybe you've heard of like the number series as like the integers, the naturals, the real numbers. Sometimes there's two R's that kind of go next to it there, right? Like there's the whole numbers. There's all sorts of different ways of illustrating these things. Maybe you've seen like Venn diagrams of them. Non-real answers would be this one right here. Like if I asked you to square root -3, that would be a non-real answer. But there's some branch of mathematics that allows you to work with the imaginary numbers, and that's I, which is this constant here. But I digress. That one's not really that important. The one we're going to focus on today is E, and E is actually a number. And so I'd like for you to find E on your calculators if you have one nearby here. It's right on this graphing calculator, it's right here. That is the letter E, and it is a constant, just like pi. See how pi is sitting right there? E is one below it, and this is E. E is a constant known as 2.71828182. And this actually is not a rational number, by the way. Like this is not repeat. It looks like it might be repeating, but if you try to turn this into a fraction, it does not turn into a fraction, right? If it actually was 2.718281828282, you could probably repeat this over and over again for a while. And I don't know if this will work, but we might try to turn this into a fraction. Oh, never mind. Okay, well, calculator wasn't able to make it into a fraction, but I promise you this is not a rational number, okay? This is an irrational number, and this is known as E, okay? And hence our title of today's notes, this is known as E and the natural logarithms. We're going to talk about this number. Did you guys know this is a number, which is about 2.71, give or take-ish. My goal today is I want to talk about its relevance, where the heck this number comes from, why it matters, and we'll talk about how to take its derivatives later. So I love the title of the notes, by the way, today. E and the natural logarithms just sounds like a really nerdy band name for math teachers. If we were to form like a math teacher's band, we would call ourselves E and the natural logarithms. So, all right, anyways, getting off topic. Let's start with this first slide. I made this first slide because I wanted to remind you of some of the rules of how to deal with exponents. So hopefully you're familiar with these. I'm not going to go over them all in detail, but here are some of the main rules. And the other thing I wanted to put on this slide here was a picture just to remind you of how logarithms and exponents are similar to each other, but they are different. They're flipped over the line y equals x. This is that line y equals x, which means that they are inverses of each other. Oh goodness, I can't spell. Inverses of each other. And so basically this point right here, your y-intercept becomes that one's x-intercept. This one goes from here to here. This one goes from here to here. They all get flipped. X and y coordinate pairs get flipped. And so there's a lot of similarities between exponential and logarithmic functions. So what I want to do is I want to begin with something that you're familiar with. I want to begin with 2 to the x, a graph that you should have covered in plenty of detail in your Math 30-1 class. When I teach this to my kids, the first thing we'll talk about is that there's one point that you should know, the y-intercept, which is at 0 and 1. And you should know that there's an asymptote that runs along the axis, because it never actually crosses there. And then from that point going forward, it basically grows exponentially. So it'll look something like this. Yeah, let's see. 0 goes through 1. Well, let me see if I can make this be a little bit more accurate, just because it's going to make a difference as we go forward. 0 goes through 1. 1 would go through 2. 2 would go through 4. 3 would go through 8. There we go. That's a little bit more. I mean, they all look roughly the same, right? But I want to make sure I get the growth factor correct. So there's my 0 and 1 right there. So there's our graph. Now what I'd like to do is just sketch a graph of what we think the derivative of this would look like. So I'm just going to pick a new color here. And I'm going to graph the derivative of this. And I'm just going to consider what what some of the main points happen to look like. So let's find let's pick a point over here. What is the slope right around here? Well, if I were to draw a slope of this graph, it's actually almost 0. Now I know it's not exactly 0 because a slope of 0 would be if it was completely going horizontal, but we know that it's getting closer and closer to the axes. But I mean, basically right here, the slope at this point is almost 0. And really the slope right here is almost 0 too as well. And all of these have a slope of 0. Oh, now the slope is getting a little bit bigger. So the slope should rise a bit more. And the slope should rise a bit more until I get right to about here, right? And if I were to calculate the slope right there, I might say, well, the slope right there is about, it looks like it's about 1. Well, if the slope is about 1, then that point should go right there too. What about here? What would the slope right there be? Looks like the slope is, I didn't draw it all that fantastic. Looks like it's slightly more than 1. Well, what about right here? What would the slope right here be? And you might say, well, maybe right here the slope is going to be, I don't know, 3 or 4. And the reason why I bring this one up is that what ends up happening is that on this particular graph right here, the derivative actually ends up looking like this. That's what the derivative ends up looking like. And you'll have to take my word for it because I don't want to show you how to find its derivative just yet. But essentially that's what the derivative looks like, is the original graph was in red, and the derivative graph, I'll call it f prime x, looks almost exactly like it, only just a little bit lower. So that ends up being your derivative of 2 to the x. Well, then if we were to find the derivative of 3 to the x, let me do the exact same thing. 3 to the x would look something like this. Actually, I think I made a mistake on this one here. No, I did that one right. Never mind. 3 to the x would look something like this. Let's see. It would also have an intercept right here. All right, it's going to have that same asymptote along the bottom here. The only difference is now it gets a little bit steeper, a little bit faster. There, it does that. Now, I know that wasn't the greatest that I did right here. But similar principles actually end up applying when we talk about... I can't change my pen color. Pen. Color. Come on, pen. There we go. Purple we'll go with. Okay, so let's do the exact same thing here. Let's talk about what the derivative would look like. Well, again, as we take these points right here, the derivative, right here, the slope is essentially 0, right? So the slope is about 0, slope is about 0, slope is about 0. Oh, slope is getting a little bit bigger. Slope is getting a little bit bigger. Slope is getting a little bit bigger. And you get to this point right here, where when you want to calculate the slope right here again, it ends up being slightly more than 1, actually, this time around when you calculate it. And so it ends up actually making a graph that looks something like this. It's also very close, but you see how the 3 to the x graph is steeper? It means the slope is actually a lot steeper as you go along. And you end up getting a scenario here where if you derive 2 to the x, the derivative of 2 to the x is just slightly below where it needs to be in order to be identical. Maybe I'm not making my point clear enough here. The derivative of an exponential graph is an exponential graph. It basically derives to itself, is the point I want to make. This red graph here is the original. The blue graph is what its derivative would look like, and it's almost the exact same as the original. And the same thing happens on this graph here for 3 to the x. 3 to the x actually derives to almost exactly the same thing, only it derives a little bit too high. Okay. One more thought. I just have a little question down here, just a thought. Why can't you derive the graph of 1 to the x? And hopefully you'll know that 1 to the x is actually literally a straight line across here, right? Because 1 times 1 times 1 times 1 times 1 is always 1. So it actually doesn't really help all that much, right? So here's my point. This means that there exists a number, and we're going to call that number e, such that when you derive the original graph, it actually derives to itself, and literally nothing changes. And e has been discovered to be this number, 2.718, which kind of makes sense as we work back through this experiment here, because if you derive 2 to the x, it derives a little bit too low. If you derive 3 to the x, remember the derivative is the purple one here, it derives a little bit too high. So if we were to derive 2.81, etc., to the power of x, and derive that number, it actually derives exactly onto itself, which is this value right here. Not 81, 2.71. I take that back. 2.718 is what e is. And so e is this irrational number, which is about 2.718. And think of it like pi. You know how pi is equal to 3.14159, etc.? Well, e is another constant, and its value is 2.71828, etc. And it's one of the 5 main constants that I talked about, the other ones being 0 and 1, which, I mean, even binary is made up of zeros and ones, right? I mean, every number is made up of a combination of some 0 and 1, except for our irrational numbers, which are pi and e. And then there's also I, which accounts for your negative square root type numbers and your non-real answers as well. So those are your main constants. So when you think of e, think of it like pi. Think of it as just it's a number, okay? And its job is that this number has come from when you derive this exponential equation, e to the x, 2.7 to the x, it actually derives to itself. So, yeah, let me show you some graphs here. Here's a graph of 5 to the x right here. And here's a graph of 1.5 to the x. What ends up happening here is that this graph right here is the only graph that its slope right here is exactly 1. When I was doing some graphing right here, I think I even drew it in right here. When I was trying to calculate the slope right there, it was about 1, but it was about a slope of 1. It's not exactly 1 over 1. It's pretty darn close. Well, that's actually what happens right here, is that this graph right here, if you were to calculate the slope of right at the y-intercept value, it's the only graph that would actually truly have a slope of 1. This one right here does not have a slope of 1. It's a little bit too low. And this graph right here does not have a slope of 1 either. It's a little bit too high. But e to the x is the only graph where when you find its slope at the y-intercept, it's 1. And that's really important because you know how the y-intercept of all exponential functions is 1? If you want it to derive to itself, it better than have a derivative which is 1 at the y-intercept, which is 1. If that makes sense. So only y equals e to the x has a gradient, which is a slope of 1 at 0, 1. All the rest of the graphs that are exponential are not quite 1 there. So, which is why it derives to itself. So this is a very unique type of function. So I remember when I was in my first year of university, I had a university professor. He still teaches there, so maybe you'll remember him. His name is Hadi Karagani, and he has quite a thick accent. And I can still remember him telling me this joke as I was learning about e to the x from him for the first time. And I love this joke. He told it so funny. His accent made it hilarious. Just the way that he told it, the inflection in his voice. And so if you ever end up having Hadi Karagani at the University of Lethbridge, maybe he'll tell this joke too. So I mean, you can read it out, but I'll read it out for you again. A mathematician went insane and believed that he was the differentiation operator. Basically, that just means that he believes that he causes things to derive. Right? He's the d over dx. So his friends placed him in a mental hospital until he got better, and all day around he would go frightening the other patients by staring at them saying, "I differentiate you." And I can still hear Professor Karagani's voice as he would say, "I differentiate you." Anyway, so one day he meets a new patient, and true to form, he stares at the new patient and says, "I differentiate you." But for once, the victim's expression didn't change. Surprised, the mathematician marshals his energies, stares fiercely at the new patient, and yells loudly, "I differentiate you!" But still, the man had no reaction. Finally, in frustration, the mathematician screams out, "I differentiate you!" At which point, the new patient calmly looks up and says, "You can differentiate me all you like. I'm e to the x." Oh, such a silly math joke, right? Hopefully you get the concept, though, right? Is that when you derive e to the x, it stays e to the x. Every other derivative that we've learned about changes, right? If you were to derive x squared, it's 2x. If you were to derive sine of x, it's cosine of x. But if you derive e to the x, it remains e to the x. It's the one function that its derivative is itself, hence this silly little math joke. So I have never forgotten that story, and I mean, it sticks in my mind to this day. So, okay, anyways, let's try some examples. Now that we've learned about the derivative of e to the x, let's try to solve this. So if I want to differentiate this one right here, the one changes is that this isn't e to the x, this is e to the 2x. Right, that 2 right there has modified this function. So this is a chain rule. If you want to do a chain rule property to find the derivative, well, you derive the original. So the original is e to the 2x. The derivative of e to the 2x will stay itself. but then we have to chain on the change, right? And it wasn't x, it was 2x. So I have to derive the 2x. I have to chain on the baby concept. So this ends up giving you e to the 2x times by 2. So its derivative is 2e to the 2x. So hopefully that made sense here. This guy right here is a chain. It's not x, right? E to the x is e to the x. E to the 2x derives to e to the 2x, but you have to chain on the derivative of the 2x because this guy right here is not actually what it should be. So some of you are really struggling on your midterm, by the way, with chain rule. So we may want to recover how to do that for that concept, because chain rule is probably the most important thing that you're going to want to know going forward. When I emailed one of my professors, not Professor Karagani, but a different one at the U of L, he said that chain rule is the thing that students struggle the most with. So if you are not comfortable with chain rule, we need to chat and try to make sure we fix that. So let's try this one here. If I want to derive this guy right here, let's even just write this out. I'll do the derivative of e to the 6x to the 3 minus 7x. So the derivative of any e function is itself. So your derivative is going to be equal to e to the 6x cubed minus 7x. But that wasn't x. It was a whole bunch of a polynomial mess up there. So we're going to have to derive that polynomial mess. Which means our final answer is going to be 18x squared minus 7 times by e to the 6x cubed minus 7x. Hopefully you can figure out how I managed to accomplish this. When I derived this little bit right here, pull the 3 down in front, times by the 6 gives you the 18. Drop the exponent down to a squared. 7x, its slope is just 7. And yeah, then I put it in brackets to make sure it was clear that all of that is being multiplied by the e there. And my personal preference, and I'm going to want you to clean up some of these equations, by the way, and do a little bit of rearranging here. My personal preference is that I like to throw coefficients in front of trigonometry stuff and exponential stuff, just to make it look a little bit clearer, because it gets pretty crazy looking. So that's why I put, on this previous example, I put the 2 over here. So previously I hadn't really cared about whether you do some simplifying and do some rearranging, but now I'm going to ask that you do something logical. So put your monomials first, put your binomials second, put your trig and your exponential stuff towards the back, just so that it looks a little bit neater. Because the last thing I want you to do is this. E to the 6x cubed minus 7x times by 18x squared minus 7. Because some people might then think that this is a term, and then afterwards you're subtracting 7, and that is not the same thing. So I think it just helps to have a logical order. So go with your constants first, your monomials, then your binomials, right? Find something logical so that it looks kind of nice. So I put my binomial here first, and then I times it by my exponential last. Well, let's try this one. This is actually going to involve 2 chain rules, because what we have going on here is that this x right here has been replaced by sine of 2x, which means we're going to have to derive the e, then the sine, and then the 2. We're going to have to do it in stages. So let me give this a try here. And then, like I've always been saying as we go along, and I need you guys to take me up on this more often, make sure you ask me questions if I lose you. All right, I can clarify things. So this is going to give you e sine 2x. It derives to itself, but then we're going to need the derivative of the baby. And the baby in this example here was the sine of 2x. Because, right, this thing up top here was not x. It was sine 2x. I have a hard time writing on my board today. Okay, so how do you derive sine? Well, sine derives to cosine. So that's going to be the cosine of 2x. So sine 2x becomes cosine 2x. But then when you take the derivative of one more thing, it wasn't actually cosine of x, it was cosine of 2x, so we have to derive the 2. So here'd be the last thing. I'd like you to put the 2 out front, because that's a constant. Now, I don't actually really care what order you put these things in otherwise for the exponential versus the trigonometric stuff, but definitely put that constant out front. I think that makes the most logical sense. So sine of 2x times by the cosine of 2x There we go. There's our derivative. So hopefully I didn't lose you there, but hopefully you can see that there are two distinct chain rules happening here. You have, it's supposed to have e to the x, but you don't have e to the x. You have e to the sine x. But it wasn't just sine x, it was 2x. So there's really like three different things you had to do. You had to deal with the e to the x portion of it. You had to deal with the sine x portion of it. And then you also had to deal with the 2 that was sitting in here, right? Because really this one was up there, and that one was in there. So it's like that Russian nesting doll example. You have a function inside a function inside another function. Okay, well, then that leads to the question, well, okay, that's fantastic for exponential functions if the base is e. Awesome. If the base is e, it derives to itself. If there's a little modifier, we just use a chain rule. But what happens if the base isn't 2.7, whatever e is? What if the base is 2 or 3 or 7 or 19 over 5? Can we still deal with this? And yes, we can. There's ways of doing it. What we're going to do is we're going to talk about how to deal with the natural logarithms, and then that will help answer our question tomorrow, or at least in the next lesson, whenever you watch this video. So I want to point out this is going to be something that we talk about in the next lesson. In order to learn how to deal with this, we have to first learn about the natural logarithms, hence our title, E and the natural logarithms. So, getting back to the way this works then, a natural logarithm then is what happens when you have your base becoming e. Remember how the base was e to the x? Well, the way we rearrange that is log base e of y equals x. Right? Like you rearrange it into something like this. Now, maybe I don't want to take the inverse, so maybe I want to flip the x and y around. Maybe I'm confusing you by doing it this way here. But let's just recap from the beginning here just to make sure I don't lose you. Remember how e to the x would look something like this? That would be e to the x. Well, it would have an inverse that would look like this. Now, if the original graph was e to the x, the inverse graph would be e to the y equals x. And we could then put that into log format by calling it log base e of x equals y. But because this is so common, maybe not up till now in your math career, but because bases of e are so common, they're so useful, that rather than calling it log base e and having to literally every time change that number to an e, we gave it a brand new name and we called it a ln, and we call it a natural logarithm. And one of the reasons why it's called a natural logarithm is that a lot of natural things, like everyday life nature stuff, actually grows according to this logarithmic function. Remember how a log graph looks something like this, where it grows slowly but surely? For example, I'd never noticed this before until my second daughter was born, and I was in the doctor's office, and they were plotting the circumference of her head. Okay, I know I'm going off on a tangent, but they were plotting the circumference of her head as she grew. And as she grew, it was supposed to actually follow a natural logarithmic curve where her head was supposed to continue to get bigger and bigger and bigger, but really as we become adults, does our head really grow anymore? I mean, if you're a sports fan and you want to make fun of Barry Bonds, then maybe you want to go there if you get the reference, steroids and performance-enhancing drugs. Anyways, but really no, like our head side does not continue to grow, so it does, like, it kind of limits out, kind of like a log graph does, where it like slowly but surely kind of peters out. It grows a little bit maybe, right? Anyways, the point I want to make is that natural stuff often grows according to a natural logarithm with that sort of base there. So trees I've seen measured with natural logarithms. And yeah, like I said, when I was at my doctor's office, she had a graph on there of how my daughter was supposed to be gaining, not only weight and size, but head circumference. And it blew my mind. I was like, that's a logarithmic graph! So, anyways, things that you notice when you're a math teacher. So, okay, long story short, this ln right here, ln, refers to a natural logarithm. It's pronounced lawn, like your front lawn, go water the lawn, go mow the lawn, and it's actually implying that its base is e. And the reason I need to show you this is that if we can use natural logarithms, we can help do the bases that are not e. But we have to get there. So I want to show you how we're going to differentiate this function here. We're going to try to find the derivative of y equals ln x, which is basically written as y equals log base e of x. Well, I'd love to be able to derive this guy, but I really can't using the rules I have. But what I can do is I can rearrange it into its other format, which would be e to the y equals x, which I've kind of written over here. All three of these statements are literally the exact same as each other. Ln x is the same as log base e. And if you rearrange this logarithm into an exponent, it gives you this guy right here. Well, now I can try to take the derivative here if I use, what's it called again? Implicit differentiation, where we derive both sides with respect to x. So I'm going to derive this side here, and then I'm going to derive this side here. Well, when you derive e to anything, it remains e to anything, except that was supposed to be an x up in the corner, and it's a y. So I have to throw an extra dy over dx on there. And then here, dx over dx, the derivative of x is just 1. Well, now I want to get my dy over dx by itself, so I'm going to divide by e to the y. I will divide by e to the y, and you end up with the derivative of 1 over e to the y. However, e to the y, if you look back up here, was actually equal to x. So your derivative is 1 over x. There's the proof for how this was created. Let me show you one more time. Ln x is log base ex. I can rearrange this exponentially into e to the y equals x. Then I took the derivative of both sides. When you derive x, it's just 1. When you derive e to the y, it remains e to the y because we know now that a derivative of e stays itself. But because this was a y up here, not an x, I needed an extra dy over dx derivative right here, which I then isolated for by dividing out my e to the y and getting my derivative, my y prime, being equal to 1 over e to the y. But look back up here, e to the y is equal to x, so my derivative, the derivative then of the natural logarithm of x is 1 over x. That's our derivative. So now there's a new rule we can use to try to solve more derivatives. So for this part of my lesson here, we're going to focus on natural logarithms. And then in the next part, the next video lesson, I'm going to show you how natural logarithms can help us finally solve this problem here of how do we take the derivative of 2 to the x and 3 to the x. How do we deal with that? But I'll get to that in the next lesson, tomorrow, whenever you watch it. So let's try this one here. How do we find the derivative here? Well, the derivative is, derivative of ln is 1 over x. So really this is 2 times 1 over x, which gives you 2 over x. Well, this next one right here is a little bit different. This is not just a constant sitting out front. It's a time sign, by the way. This isn't just a constant out front. This is actually a product rule. So to find this derivative, it's going to have to be the first times the derivative of the second plus the second times the derivative of the first. Okay, so that'll be 4x, and then the derivative of the natural logarithm is 1 over x. We just learned that. And then here we'll have ln x, and we'll have to times it by 4. Clean it up a little bit. That'll cancel, so I'll just give you 4. And then that'll give you 4 ln x. There we go. There is our derivative. One more thing you could do, you could also, you could factor, by the way. You could do 4 bracket 1 plus ln x. One more option here, if you remember your exponent rules. This ln, this natural logarithm, is a logarithm, so all logarithm rules still apply. You could actually make it ln x to the 4 if you wanted to. Remember how you can drop the exponent down in front? That's also valid here too. So this would also work. I would like you to at least get it to something that looks like this. Do not leave it in this format here. Do a little bit more cleaning up to make it look kind of nice. Okay, go back and rewatch that if you need to. Make sure you ask me lots of questions. Make a list of questions to ask. I really need to say, make sure that you are meeting with me video conference-wise or in person or however it works. But you got to meet with me at least a couple times a week here to talk. Many of you are trying to do this on your own, and you're probably not doing as well as you'd like to. And I think that's the biggest reason why is that you need to start learning how to advocate for more help. Especially when you know you need it, because you're going to hit a wall in university where it's going to get harder. And you can't just, well, I'm a 90 student, I always do well, because everybody is a 90 student, right? Everybody that's going to be in your classes, they are all honor roll kids. And yet, half of them will fail. And I don't want you to be in that half. I want you not only to learn how to do calculus, but I also want you to learn how to advocate for yourself, how to figure it out, how to learn how to be a learner, how to learn how to be a student. And so I am your resource. You need to make sure that you come find me for help on a regular basis. And not even when you think you get it. Even when you think you get it, you should still talk to me and make sure and say, okay, I just want to be clear. Can you look at this example and make sure I understand it? Because, yeah, when you get to university next year, there is no classroom, there is no accountability, there's no attendance. You're on your own. And that's why so many students often struggle. So I really want to encourage you in this last half of our semester here, make sure that you learn how to ask for help. Make sure that you learn how to find resources at your disposal. So you have me. Email me, video conference me, but let's make sure that we chat, okay? All right, rant over. Let's try this one here. If I want to derive this one here, this is a product, not a product rule, this is a chain rule. See how there's a baby hidden inside that logarithm? So the way this works is that it's 1 over top of x, but your x is not actually x, it was x squared minus x. Right? The derivative of a natural logarithm is 1 over x. But this guy right here is really what our x was, right? So it's 1 over that stuff there, but then we have to times by the derivative of x squared minus x. Which means it needs to be 2x minus 1 over x squared minus x. There is our derivative now. So, wow, I kind of went through that a little bit fast. It seemed like that maybe went a little bit too quickly. Let's re-talk about this one more time. The derivative of a ln, if you derive it, is 1 over x. But if you have something else in this location, it has to get put down there. So since this wasn't x, it was x squared minus x, that went down there. And then the chain rule then says, well, then you need to chain on the derivative of that baby inside, which will be 2x minus 1. And I just kind of put it all together in one big piece and said, well, then this 2x minus 1 I'm going to attach to this 1 up here, and then I'll leave the x squared minus x on the bottom. Now, you could try factoring the bottom, because hopefully it's pretty clear that you can factor out an x. But unfortunately, that does not cancel. You can't try to do that. That would be very bad. So you may as well leave it here. So, okay, again, if you have questions, please make sure you ask me. Even if you don't have questions, still ask me. So that's the end of this lesson here. I would highly recommend, if you get a chance, move right into the next lesson almost, because the next lesson is basically going to answer the question of, well, what do we do when we have these guys right here? What happens if the base is not e? And what happens if it's not a natural logarithm? So, okay, I'll stop the video now. Get a hold of me, guys. Make sure you learn how to be a student. Okay, you're not all the way on your own right now. You have me to help, but you have to ask. I can't hunt you down. I'm trying to, but I need you to ask me for more help, because if you want to get those really high marks, that's what it's going to take. So, okay, we'll talk to you later.